Welcome to the Problemas channel Season 2 Episode 10, the episode in which we will discuss the solution of the mathematics problem S2M12. Before we do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then it is a good idea to go to the channel's homepage and in the channel's trailer section find the episode titled The Problemas Channel How-To and watch that episode in its entirety, because in that episode we explain and motivate everything that we do on this channel. I have titled this episode Zero in the Midst because in the mathematics problem S2M12 we're given a sequence of real numbers that is defined via the following recurrence relation. X sub n plus 2 equals x sub n minus 1 over x sub n plus 1, and we're also given two quite poetic values of the first two elements of that sequence as 20 and 25. The author of this problem is convinced that somewhere in the midst of these real numbers there sits a zero, and this is our intellectual challenge. That is, our mission, should we choose to accept it, is to show that there exists a whole positive number n such that x sub n is 0, and we're also asked to find the value of this whole positive number. Depending on the type of school that you are attending, you may actually run into this problem late in the high school if you're taking the introduction to mathematical analysis. Or, for example, in my time, that was a typical problem during the first semester, first year in the course titled Mathematical Analysis. In your country, that problem may show up in a course that is titled differently, but the name of the course does not matter. What matters for us is the mathematical and technical essence of the given problem. So what is that essence? Well, as mathematically inclined thinkers, when someone, or actually anyone, tells us anything, we're always skeptical. Just because someone said something doesn't mean that that is true. And in respect with these statements, we're always looking for two things. First of all, we want a convincing line of reasoning or a proof, and ideally we want a beautiful, elegant, crisp, motivational story behind that proof. How did someone manage to come up with that line of reasoning? Here in this problem, someone claims that eventually in this sequence of real numbers, a zero will pop out. Is that true? Yes, no, maybe. Is there any chance that this will happen? Well, unleashing a brute force on this here puppy without thinking too much, we see, okay, if x sub 1 is 1, forget about these initial values over here for a moment. As such, if x sub 1 is 1 and x sub 2 is 1, what do we have? 1 minus 1 over 1 is 1, which is 1 minus 1 is 0. Maybe. So now that we think that the claim in this problem is somewhat plausible, we unleash the reverse order problem solving approach on this problem. Again, if you're facing this type of problems for the first time, it may be intimidating, but as we shall see momentarily, the problem is not really that intimidating, and it's not that scary, and it's not that complicated. We know that the reverse order problem solving approach has two main flavors, the mechanical flavor and the heuristic flavor, and none of these flavors actually provide any algorithmic guidance for the generation of the convincing line of reasoning sought after. But by the looks of it, because we have a nice and crisp relation, or some people will say a formula, that ties together the elements of the given sequence of real numbers, we can use the mechanical flavor of the reverse order problem solving approach. That approach suggests that we begin searching for a solution of the given problem from the end, so to speak, or from the final state. What is the final state or the end in this specific problem? Well, let us assume for a moment that the claim in this problem is indeed true, and instead of a question mark shown over here, indeed a whole positive number n such that x sub n is equal to 0, that number does exist. This condition or this assumption is our final state or the end of the problem. As such, we now play with the given relation named and numbered over here as 1, because we want to bake this specific assumption or this condition into that given relation over here. In order to do that, what kind of maneuver can we execute? Well, we take our whole positive number n, the usual suspect, and we perform the following maneuver with respect to the relation shown in 1. We say that n becomes uppercase n minus 2. And what does that mean? If we take this value of n and insert it into the relation shown over here, numbered 1, what will happen? Well, n plus 2, if we add 2 to either side of the equal sign, what will we have? We'll have x sub n. Then on the right hand side of the equal sign over here, what will we have? Well, we take the value of the n verbatim. We will have x sub n minus 2 minus 1 over what? Here we have the expression n plus 1. We add 1 to either side of the equal sign over here. What will we have? N minus 1, and that's what we write down. X n minus 1. Again, this specific maneuver is not that complicated. We simply took the assumption in this problem that a whole positive number n such that x sub n is 0 exists, and we pretty much rephrased the given recurrence relation in the terms of that assumption. So now this whole expression should be 0. Again, this is not given, this is our assumption. This is the reverse order problem solving approach in action. We're taking this statement over here as our initial assumption, and as we shall see momentarily, we'll be working backwards. Before we do that, however, how much and what type of tactical information can we squeeze from this relation over here? Well, forgetting the left-hand side of this expression for a moment, what do we have? Well, we have two summands equal to 0. If we rearrange this equality slightly, what will we have? We'll have x n sub n minus 2 equals 1 over x n minus 1. That much should be easy to comprehend by everyone. And now we multiply both sides of this equality by the element called x sub n minus 1. And what do we have? We have x n minus 2 times x n minus 1 equals to 1. X sub n minus 2 times x sub n minus 1 equals 1. Again, why is this string of maneuvers legal? Well, we assume identically here that the whole positive number uppercase n that we're looking for is the first number for which the element 0 shows up in the sequence and no zeros show up prior to that. That is why we can divide by the element called x sub n minus 1, and because that element is not 0, that division is legal. Thus, we frame the following if p then q implication. If x sub n is 0, then this product over here of two consecutive elements in that sequence must be 1. Conversely, will that implication hold true? Well, we assume for a moment that a product of two consecutive elements of the given sequence is 1. Then what do? Well, we divide both sides of this equality by the element x sub n minus 1. We arrive at this relationship over here, and from both sides of this equality we subtract this element, we arrive over here, and we see that this transition from here to here brings us exactly to the element x sub n, and we can write that the element x sub n equals to 0 if and only if the product of two consecutive elements of the sequence shown over here is 1, and the IFF, or if abbreviation, stands for if and only if, which is basically another shorthand notation for two implications that work both ways. If P, then Q, and if Q, then P. In other words, if x sub n equals 0, then this product over here is 1, and conversely, if this product of these two elements is 1, then x sub n is equal to 0. And what does that mean? Well, over here I moved the relation that we deduced earlier from the top of the board over here, and in order to see what does that mean for us, we try to iterate this relation over here. Let's name it 2. We iterate it once rightward by replacing in that relation n with n plus 1. What will happen if we replace n with n plus 1 in the relation shown in 2? Well, we will obtain on the left hand side of the equal sign x sub n plus 1 equals to n minus 2 becomes n minus 2 plus 1 n minus 1 x n minus 1 minus 1 over what? If we replace n minus 1 with n plus 1, then we will obtain precisely x sub n. And we already see that under the assumption that x sub n is 0, this number over here is 0. This operation is illegal. Division by 0 is not allowed. And what kind of conclusion do we draw from here? Well, for any whole positive number lowercase n greater than n, for any number such as this, no element of this sequence of real numbers is defined, because to obtain all such numbers we have to go through division by 0, and that is not allowed, that is illegal. And what kind of conclusion do we draw from this? Well, by the looks of it, under the standing assumption, our sequence of real numbers must be finite, and it will look as follows. Let's write it down over here. It will be x sub 1 comma x sub 2 comma x sub 3 something else, so on, and here it will be what? X, for example, n minus 3 comma x n minus 2 comma x n minus 1 comma and x sub n, and this is it. And what do we do with this sequence of real numbers? Well, this is another opportunity to see how the reverse order problem solving approach works. We'll see it in action in a moment, but our overall idea is to combine this unit of mathematical knowledge that we deduced with the relation that we have here in 2, and think about it for a second, precisely work our way backwards by looking at the products of immediately adjacent elements in the sequence, but in reverse order, starting from the logical end towards the logical beginning as follows. Here, let us execute the following maneuver. We will loiter around the relation number 2 shown over here. Forget about for a moment that xn over here is 0. We will use this relation for utilitarian purposes only. We'll operate it quite formally, but we will multiply both sides of this relation by the elements shown in the denominator over here. Multiply both sides of this equality by the element named x sub n minus 1. And once we do that, what shall we have? Let's write it down. We will have x sub n minus 1 multiplied by the element named x sub n. Wonderful. Over here equals to what? It will be the element x sub n minus 2 times the element x sub n minus 1. Here we will have minus 1. And now, do you see anything familiar over here? We will see the product of these two immediately adjacent elements over here. And we will simply rewrite this equality by moving this product to the left-hand side of this equation, and by moving this product to the other side and balancing the negative ones across it, and we shall obtain. Another way to look at it is simply to move this negative one over here and then rewrite this equation the other way. So we will have x sub n minus 2 times x sub n minus 1 equals to x n minus 1 times x sub n plus 1. This string of manipulations should be straightforward. Everyone should be able to comprehend it. It's not that difficult. At this point, it's nothing more than middle school symbolic shuffling. This, in some sense, this is not mathematics. The mathematics with the capital M over here was a happy thought, or the ability to generate the happy thought to analyze the sequence in reverse order. That is mathematics. Now, right now, mathematics is standing aside a little bit. Here is arithmetic. So now, once we have this relation, why did we obtain it? Well, we see that when x sub n is 0, then this product over here of these two elements is 1, as shown over here. But the whole idea now is to iterate the value of n, iterate this value of n by 1 leftward, so to speak, from the larger values towards the smaller values as follows. Here I took the liberty to move the relation that we just deduced over here to that side of the board, and I gave it the name 4, or the number 4. And the main idea now is to iterate that relation, the relation number 4, leftward by gradually and carefully decreasing the value of n by 1. In other words, what will happen if in 4 we replace n with n minus 1 uniformly across the board, so to speak? Well, let's write down the result carefully. N minus 2 becomes n minus 3. So we have x n minus 3 times n minus 1 becomes what? N minus 2. Correct. So we write x n minus 2 equals 2. N minus 1 becomes what? N minus 2. X n minus 2 times. What does n become? Well, we're replacing n with n minus 1, so n becomes n minus 1, x n minus 1 plus 1. There is no variance in the last summoned in 4. It goes in verbatim. But now, what kind of magic do we witness? Well, we witness the fact that on the right-hand side of this relation, we have the previously computed product of two immediately adjacent elements of the sequence of real numbers that is given. So if we inject 1 over here, and what do we have? We have 1 plus 1, and 1 plus 1 is equal to, very well, that is 2. And we keep iterating the relation shown in 4 leftward by gradually decreasing n by 1. But again, tactically, it is slightly more advantageous to work with the previously obtained relation over here. So in this relation, we replace n with n minus 1, and we write down the result. What do we have? We have x, n minus 3. We subtract 1 from this index, and what do we get? N minus 4 times x n minus 3. We're reducing this subindex by 1 equals to what? X n minus 3 times what? X n minus 2 plus 1. Still, 1 does not change, so this is the relation that we get. Again, this transition from here to here and from here to here, again, should be very transparent. We simply replaced uniformly the value of n over here and over here, carefully and in steps by 1. But now what do we see? We see that here we have a product whose value we already computed over here. So this guy goes over here, and what do we have? This value is 2, so we have 2 plus 1. This is very complicated. So what is the answer of 2 plus 1? It is 3. Yes, very well. We write down 3, and we keep going. We now take this relation over here and iterate it leftward once carefully by replacing the value of n with n minus 1 uniformly across the board. What do we have? We have x n minus 5 times x n minus 4. We're basically subtracting 1 from each sub-index. And what do we have on the right-hand side of this relation? X n minus 4 times x n minus 3 plus 1. And what kind of magic is waiting for us over here? Well, the value of this product, this guy, was computed in the previous step right here. So this guy goes over here. We take 3 plus 1, 3 plus 1. Another complicated task is 4. And we do not stop, as the reverse order problem solving approach prescribes. Here we carefully roll backwards by 1, and we're examining all these products of immediately adjacent elements. You want to do another one? Okay, let's do another one. So in this relation over here, uniformly and across the board, we replace the value of each index n with n minus 1, one smaller. What do we have? We have x n minus 6 times x sub n minus 5 equals to x what? N minus 5 times x what? N minus 4 plus 1. And we already expect the magic to work. The value of this product over here was computed by us on the previous step, courtesy of the reverse order problem solving approach. We take this guy, slug him in here, and what do we have? 4 plus 1, 4 plus 1, another challenge, that is 5. And we can keep going like this, but will this process, will the reverse order problem solving approach, so to speak, happily roll over this element and keep going, or will it stop? Well, we reason that it will stop at some point. So here we'll put the dots to designate that we keep doing this process over and over again. But at some point we terminate with the product of x 1 times x sub 2, which must be equal to what? What do you guys think this product over here should be? Well, we just need to, technically, we need to count the number of immediately adjacent products of the elements of our sequence. How many such products will be written on the board if we knew, for example, the specific value of n? What do you think? Counting various arrangements of objects is another wonderful corner of mathematics, and it offers plenty of opportunities to show off and exhibit your creativity, ingenuity, and improvisational skills. And different people count things in different ways, which is a wonderful thing. You guys are invited to do it your own way. Here is my idea for demonstration purposes. This is not the only way, but just as one way. Notice that here we are pairing up the elements in the given sequence as follows. For example, looking at the product shown in 3, where can we find this product in the sequence written over here? Well, this is this happy dynamic duo. This guy, I'll mark this duo with the yellow bracket. This is the product of 2 immediately adjacent elements of the given sequence. What about these 2 guys in the next product over here? Well, the same element over here, notice this guy, he participates in the next product right here, this guy. What about this product over here? Well, we do not show him explicitly, but you understand. It will be this pair right here, so on, and then it will go as follows. At some point there will be product x2 times x3, and our final product is x1 times x2. So how can we count how many such products are here? Well, notice here that the way we wrote these numbers down, we separated them with a comma, and what kind of pattern do we see when it comes to commas and our brackets? Well, we see that at each and every single comma in this sequence belongs to precisely one bracket, or participates, so to speak, in precisely one product. And we also see that no single comma is left out, or no single comma does not belong to any bracket, and no single comma belongs to more than one bracket. In other words, each and every comma over here belongs to precisely and only one bracket. Consequently, the number of commas over here in this list must be equal to the number of brackets. The number of brackets is equal to the number of products of the immediately adjacent elements in this sequence, and the number of such products is basically the number of lines that we wrote down on the board. And all this counting magic amounts to what? How many commas will be in this sequence over here if we do not know the specific value of n? Well, it will be precisely n minus 2, shown over here. So here, this product will be n minus 2. Consequently, we see that, for example, if we step forward a little bit, x2 times x3 will be what? It will be n minus 3, and so on. But again, what we want to emphasize in this episode is the mechanics of the reverse order problem solving approach, where we started from the final state of this problem, which was designated by this element, and we rolled through that sequence in reverse order from the higher numbered elements of the sequence towards the lower numbered elements of the sequence. We counted the number of all products of the immediately adjacent elements in that sequence pretty much by exercising the given recurrence relation. We counted the number of such strings on a board as n minus 2. Consequently, from here it follows what? That the number n, this is our big result, will be equal to x sub 1 times x sub 2 plus 2. This is our result. Let me write it down over here, and we see that now that we understand the mechanics of how the solution of this problem can be generated, the actual values over here for the first two elements in the sequence do not really matter. This is the workhorse formula, so to speak. And again, as I mentioned in the previous episode, the reason I chose this poetic, so to speak, values of 20 and 25 is because the year in which I shoot this episode is 2025. We cut this year in half. We have 20 on one side, 25 on the other, and there you go. And just for completeness, what will be the answer in this case? Well, 20 times 25 is 500. 500 plus 2 is 502. Consequently, we write down over here, maybe let me use the red chalk just to make it more visible. Where can we do it? Let's do it over here. We'll write n equals 502, and we'll play with this number a little bit in the next segment. Now that we know the specific value of the whole positive number and that turns the corresponding element of the given sequence of real numbers into 0, we can play with this number a little bit and we can compute the first few elements of that sequence. For example, the value of the next element after the second one, x sub 3, this guy right here, will be given by this expression. And once we play with numbers, we get this scary looking fraction. Once we know that value, we can compute the value of the next element, x sub 4. This arithmetic over here looks even more frightening. The moment I see these numbers, they make my liver quiver. But this is the wonderful thing about mathematics. If someone decides to take on this computation and keeps going with the consecutive values of the elements of the sequence, our claim is that on the element x sub 502, they will step precisely on 0. And judging from the master formula that we obtained in this problem, if you want to give this problem or similar one to your students, then obviously we understand that the specific values over here will depend on your choice of the values for the first two elements in that sequence. Now that we solved this problem, we want to emphasize the fact that yes, you can count the number of consecutive products in this particular case in a number of different ways. In the big scope of things, it doesn't matter. What matters is the mathematics of this problem, or the ability of us as problem solvers to generate the happy thought to attack this problem using the reverse order problem solving approach. And pretty much all the symbolic shuffling that followed that idea was not really mathematics. It was more of a computational calisthenics, and computational calisthenics, as we mentioned in season 1, episode 1, is not mathematics. Even though we use very straightforward material in order to explain how the reverse order problem solving approach works, the material that was very straightforward and at the level of perhaps middle school, maybe high school, and did not require any prolonged, highly specialized training. It doesn't matter that the reverse order problem solving approach is not useful and important. It is, for example, depending on who you ask. Some people will say computer science, some people will say mathematics. Again, in the big scope of things, it doesn't matter. But for example, the notion of backward induction is a real deal, is a real thing in grown-up mathematics. And in the near future, we'll see, for example, how the reverse order problem solving approach may play out in physics in general and in classical mechanics in particular. This is not only it for this problem, but this is also it for our initial study of the reverse order problem solving approach. Starting with the next challenge that I'm about to present, we will begin the study of the of another problem solving approach that I titled space-time. It sounds a little bit sophisticated or too highbrow, but it's not. This is the best thing that I was able to come up with. Maybe you will come up with a different idea, but we will begin the study of the space-time problem-solving approach by using a problem that is actually more than 1,000 years old. Amazingly enough, our next challenge that will signify the beginning of the study of the problem-solving approach, to which I refer as space-time, is no less than at least 1,200 years old. In order to paint a little bit of a historical background with broad strokes, as a thought experiment, let us pretend that we transported ourselves back in time into the middle of the 8th and the beginning of the 9th century Common Era in apparently Western Europe, where at that time there was a very prominent figure who went by this name over here, spelled out apparently in Latin. I will not venture to pronounce this name in Latin or any of these names for that matter over here, because all these names are beyond my linguistic capabilities. Hopefully you guys know better how to pronounce these names, but apparently he was a big time ruler, big shot. He affected the overall historical development of Western Europe in particular, and perhaps even Europe in general. This is again his name. This is the time where he lived during the Common Era, and around year 795 of Common Era again, he made this German city the capital of his empire. And again, there will be some number of extremal claims over here. I always take these claims with a grain of salt. It's not really sure how can we validate and prove that this indeed was the case, but apparently this gentleman over here in this here German city issued an order to create the first educational organization in Western Europe. Call it a gymnasium, call it a college, call it a university, it doesn't really matter, but fundamentally, out of total absence, apparently, of such educational organizations, this big shot guy said, okay, let's do it. Also, right around this time, right here in Western Europe, in the court of this gentleman right here, there lived another scholar, let's say. Again, his name I spelled out over here. This, I think, I'm not even sure, that's probably English and some mix of Latin. That was his name. I will not venture to pronounce it, but the bottom line is that right around this time, for the construction of the first educational organization, this gentleman published the book that is titled over here. Again, I spelled it out in Latin. I will not venture to pronounce it. But in that book was a collection of problems to which some people refer as recreational mathematics. But as we now know, there was literally nothing recreational about it. Some problems in this book actually led to very deep mathematics as we know it today. Again, depending on who you ask, this book had 52 to 56 problems. And again, I'm not sure how these claims can be verified. The number I heard was 52, but again, it doesn't matter. Apparently, what we can agree on is that under problem number 18, our problem that we will take on for our next challenge, and which I titled S2E10, was published back then. And in my words, in English, the title of that book basically means a collection of problems for the intellectual development of young people. Now, that's the gist of it. I will also not argue with you guys if you disagree with me and you think that this should be really a computer science problem. Be my guest by all means, but for bureaucratic purposes, I named the problem S2E10 as a problem in mathematics. And the way this problem goes, actually, apparently this problem was born more than 1,200 years ago. Once upon a time, in some village, there lived a peasant, and he traveled from point A to point B with the happy company of a goat, a head of cabbage, and a wolf. At some point in his journey, he came to a river. miraculously there on the bank of the river there was a boat, but the trick is that the boat could fit at most two objects or two items. Obviously it can fit 1, 0, or 2, 2 at the most, and no more than 2. The challenge is that the peasant has to cross the river, but there are two incompatibilities in his happy company. What does incompatibility mean? Incompatibility means that if a goat and a head of cabbage are left without the adult supervision, then basically the goat will eat the head of cabbage, and likewise if a wolf is left in the company of a goat without the adult supervision, then the wolf will snack on the goat, and that's not a cool thing. And there lies the challenge. Come up with an algorithm or with a solution, description, finite description of a finite number of steps of how our peasant can cross the river using the boat with the smallest number of crossings in such a way that each and every member of his merry company is left intact. In other words, let's say our peasant is on this bank with his merry company. We want him to do something with the boat and the members of his team and wind up on this bank over here with the goat, the head of cabbage, and the wolf all intact and happy traveling onward. Now, this problem is discussed in all sorts of computer science books on algorithms and the design of algorithms. But what I would suggest is when you take on this problem, then try to think and try to crystallize exactly the technical core of what essentially exactly is going on with the solution of this problem when we come up with it. This is it for this episode. Good luck. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will discuss the solution of the problem S2E10.